In this video, we're going to discuss the fundamental theorem of calculus part 2. There's actually two parts. In Calc 1, we only discuss this part of the fundamental theorem. So here it is read. If f of x, little f of x, is a continuous function, and capital F of x is any antiderivative function of little f of x, then the definite integral from a to b of little f of x dx is equal to capital F of B minus capital F of A. All right, so that's a huge mouthful and it's very, very important, but when you're first trying to wrap your mind around this, it can be a little bit difficult. So let's go ahead and try to understand this by way of an example, first of all. So I'm going to take a simple function here for us to work with. We're going to consider the function little f of x equals 2x. So notice in this fundamental theorem, we have two functions going on, little f of x, which is the function we're going to integrate, and capital F, which is the antiderivative. So if little f of x is equal to 2x, then what is its antiderivative? What is the function that when you find its derivative gives you 2x? Well, there's lots of functions that could be, right? Capital F of x could be x squared, because the derivative of x squared is 2x. Capital F of x could be x squared minus 7, because the derivative of that is also 2x. Capital F of x could be x squared plus 13, because the derivative of that is 2x. In fact, all of these are just examples of specific antiderivatives. In general, the antiderivative of f of x is x squared plus c, where c could be any constant number. So the fundamental theorem of calculus is telling us that if we want to find the definite integral of 2x, then we first need to understand what its general antiderivative is, which is x squared plus c, and then we need to evaluate that general antiderivative at x equals b and at x equals a and subtract. The fundamental theorem of calculus is telling us that the definite integral of little f of x from x equals a to x equals b can be calculated by evaluating its antiderivative at b and a and then finding the difference between the two values. In other words, this definite integral tells us the change in height of the antiderivative function capital F of x from x equals a to x equals b. So let's go ahead and take a look at this actual calculation. We want to go ahead and calculate the definite integral from 7 to 9 of this little f function 2x. So the definite integral from x equals 7 to x equals 9 of 2x dx. So the first step is to go ahead and find the antiderivative function of little f of x. So we know that in general, the antiderivative is x squared plus c. But it doesn't matter what c is equal to. When we evaluate it at 7, and then we evaluate it at 9, and then we subtract, we would be subtracting c minus c, and it would cancel. So in general, when you do this first step and find the antiderivative, you can just let c equal 0, because it's going to cancel when we do the subtraction anyway. So I found the general antiderivative, but then I let c equal 0. So the antiderivative I'm going to work with is x squared. I then need to calculate the value of this antiderivative at x equals 7 and x equals 9 and subtract f of 9 minus f of 7. So I take x squared at 9, so 9 squared, and x squared at 7, so 7 squared, and then subtract. I get 81 minus 49, which is 32. So what did I just calculate when I did this? Two things, two ways we want to think about that calculation. So first, one way to think about this calculation geometrically is to think about what it means on the graph of little f of x equals 2x. If you graph y equals 2x, it's a straight line, and we are looking at that from x equals 7 to x equals 9, and that definite integral is calculating the area between the x-axis and that rate function y equals 2x between x equals 7 and x equals 9. So this area here, apparently that area is 32. Another way to think about it geometrically is to think about the graph of the antiderivative function. If you think about the graph of capital F of x equals x squared, it's a parabola. We're considering it from x equals 7 to x equals 9, and it turns out on that span, the function y equals x squared increases 32 units.